This is the video key for the Unit 2 take-home test. Please make sure as you're using this video key, you're using it helpfully. Okay? You use it to correct your work. You will learn more from fixing a mistake that you made than from getting the answer from this video. So try and make sure you're using this the right way. There are 10 points of extra credit hidden in this video. If you watch the whole thing, you can get those. Anything you see highlighted in green is something we're going to do together in this video. Anything that you see highlighted in yellow, I'm going to leave for you to try on your own. Alright? So let's look at our vocabulary for this unit. Really important vocabulary. The whole point of our electron configuration is telling us where electrons are arranged. So the periodic table being pulled apart in this way is showing us where those electrons are in terms of levels and sublevels. Ground state, okay. We'll look at this one. An atom's blank is a measure of how much it wants additional electrons. Okay, well, I guess the next one. The blank energy is the amount of attraction an atom has for its own electrons. So these two concepts are very, very similar, but we need to be able to tell them apart. Okay, so both ionization and electronegativity are about attraction to electrons. The difference is an atom's attraction to its own electrons. How much it wants to keep what it already has is, i.e., ionization energy. How much an atom wants additional electrons or extra electrons is electronegativity. So an atom's blank is a measure of how much it wants someone else's electrons. Extra electrons would be electronegativity. Oh, almost fit in there. Okay. An amount of attraction it has for its electrons, the ones it already has, i.e., is ionization energy, I.E. Okay. So that gets us to there. Find those other ones on your own. Okay. Hopefully we're pretty good with electron configuration by the time we're looking at this video tutorial. Otherwise, go back and look at some of the other homework ones. We're going to do oxygen together. So I'm going to get out my little sparkly placeholders. Okay. If oxygen is the point of the problem, I'm going to put one there so I know I'm stopping at electron 8. And I'm going to put one here to show me where I'm at. Okay. So the electron arrangement, the electron configuration, is that the first two electrons, if I go to the end of that block, are both in the 1s orbital. So I would say the first two electrons are in 1s, like this. Okay. After electron 1, 2, we talk about 3 and 4. And those are the two electrons in 2s. The two electrons in, 2s. That's why I wrote in pencil. After 4, I'll come to 11. 1, 2, 3, 4, 5. Okay. I'm going to say these last 4 electrons, 5, 6, 7, and 8, P4, are the 4 electrons in 2P. So if you add up those superscripts, okay, 2 plus 2 plus 2 plus 4, those are where oxygen's 8 electrons are arranged. The difference for noble gas notation then is that's our shortcut. I'm allowed to take a noble gas as a shortcut. So this is not the alkali metal shortcut. This is not the halogen shortcut. It's the noble gas shortcut. So it has to be from one of the noble gases, which are family 18 on the periodic table. I'm just going to turn this over and remind you that helium is part of family 18, even though it's in the S block. So I moved it over here. Okay. So if potassium is where we're going, it's 19 electrons. What's the biggest shortcut I can take? Well, noble gas 2 would be a shortcut. I could say noble gas 10 or noble gas 18. I couldn't take a shortcut from noble gas 36 though, because we're not there. So I'm going to say, okay, argon is going to be my shortcut. I'm going to start from there and write the symbol of only a noble gas, Ar, and that represents the first 18 electrons. And then I say what comes after 18, 19. And potassium's 19th electron is in 4s1. So that shows me my 18 electrons that are like argon plus one more is 19 electrons. Full arrangement, noble gas shortcut. Orbital notation then is what we're looking at with the arrows. Don't use arrows for anything else, but we use the arrows to represent electrons, and we use them in opposite spins, okay, which is one of your vocab from the top of this page. They have to be in the opposite direction according to the Pauli exclusion principle, if you want to feel fancy. Okay, so sodium is where we're going. Sodium's 11 electrons, and I would say the first two are in 1s. So sodium's first 2 electrons are in 1s. Now I've seen a lot of my students this year on homework write 1s2 like that. Technically that's not included in this notation, but I don't think we'd mark you wrong for putting it there. But s's have 1 orbital per sublevel, so we'll go like that. The next 2 electrons are in 2s, so anytime I put an s orbital, I get 1. Okay. Now I don't go 1, 2, 3, 4, 11, 12. No, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over here. So then I'm going to 2p. And our S, P, D, F have 1, 3, 5, 7 orbitals or bedrooms. So if I write the letter P, I'm going to put 1, 2, 3 orbitals after it. Okay? After electron 10, we come over here to 11, and that's in 3s. So I'm going to come back with my arrows and say 1s2 would be an up and a down arrow, because they'll share an orbital, with opposite spin. 2s2, up, down. 2p6, we say up, up, up. That's Hund's rule. Each electron will get its own orbital before it has to share. Opposite, down, down, down. And then we stop at 3s1 for sodium right here. 3s1. There's only 1 electron there. So if we count our arrows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 arrows are sodium's 11 electrons. That's how we represent them. Okay. I want to look at what it is in multiple choice form. And I tell my students this all the time, whether I'm teaching ACT prep classes or chemistry, take out the garbage. Okay, we want to eliminate wrong answers. That's our best bet on multiple choice tests of any subject. Okay, people, seriously. Noble gas notation for nickel. Nickel is Ni, it's number 28. It was on your symbols list, so hopefully you know that one. Okay, the noble gas shortcut would have to be from a noble gas. If we're talking about 28 electrons for nickel, I can't take a shortcut from 36 electrons. So argon is going to be where I take my shortcut from, which means I can come through and take out some garbage. I can't take a shortcut from Kr. Can't take a shortcut from Kr. So I take out the garbage. Those are garbage answers. I know my shortcut is going to be from argon. Let me grab a different color here. Okay, I know it's going to be from argon, but I don't pick the first argon I see. I have to make sure which one's right. So after electron 18, I have to come and talk about 19 and 20, because we count in order, low to high. 19 and 20 are in 4s2, but this one doesn't have 4s2, which makes me think it's wrong. After 4s2, then I go to 3d8. So I took out my 3 garbage answers. That left me with my most correct answer there. Do the same process for 6, 7, and 8. And take a look at what we did on the bottom for page or number 9 there. Okay. If you need more time on that, rewind it, pause it. Otherwise, let's move to page 2. Okay. Current model of the atom right there. Some other stuff for you at the top of the page. But let's look at 12 and 13. So number 12 says the electron configuration 1s2, 2s2, 2p2 belongs to the element blank. So I highlighted 2p2 because the last orbital gives us our biggest hint about what element we're talking about. Because the electron 2p and P2 would be electron 6, which is carbon. So I can pretty confidently say, well, that belongs to carbon. Okay, now be careful. It is not in group P2, right? We have to turn our periodic table over to see the group and period numbers here. So groups, do not forget. Whoops, and you know what? I wrote this in the wrong spot, didn't I? I meant to write it here. There we go. We're doing number 12. Groups run vertically, and periods are horizontally. Don't get those backwards. Carbon is in group 14 or 4A. If you wrote 4, you'd be wrong, because that's titanium's group is group 4. Carbon is 14 or 4A only. And it's in period, let's see, 2, right there. For number 13, the electron configuration notation for, again, I'm just going to pay attention to that last one that they tell me, 3p5. And I'll move over to this side. 3p5, right there, that would be electron 17, which is chlorine. So I'd say chlorine. I know it's not fluorine, because that would be 2p5. Bromine would be 4p5. Calcium's 4s2. That's definitely not it. Okay, so there's my answer. Okay, we're going to look at 16 and 17. A couple things that are a little bit nasty about number 16. Excuse me. I had someone pronounce this Aruba this year. True story. Cracks me up. It's Aufbau's principle. You do not need to know that Aufbau's principle says electrons fill up from low to high energy, but you just need to know that it's breaking a rule. Which of the following is incorrect? Which of the following is breaking some kind of rule? The other thing that gets hard about this is it's a lot of stuff squished together. Okay, so we're going to compare them vertically. Compare them to each other. A, B, C, and D all start with 1s2. So I can pretty confidently say that's not going to help me. They all say 2s2. They all say 2p6. They all say 3s2. Now C is over. That is just fine, because that means C is magnesium, Mg. It's not wrong, it's just a smaller element. Okay? Then they all say 3p6. They all say 4s2. And then, this one says 4p5 next. Okay, I can't go from 4s2, which is 20, to 4p5, which is 31 through 35. So that one skipped all of our 3Ds. So I'd say this one skipped the 3Ds. It's breaking a rule, so this one is breaking Aufbau's principle, or this one looks incorrect. 17 sometimes freaks people out, but 17 is almost the same question as 13. Okay? Where instead of saying 1s2, 2s2, we did 1s, 2 arrows, 2s, 2 arrows. So again, we only need to key on the last orbital, 3p1, and 3p1 belongs to aluminum down here, 3p1. So what element is it? I would say Al, aluminum. Okay. The rest of this page, important vocabulary. I'm going to offer our first little bit of extra credit right here for number 19. If you draw this, number 19 says this orbital notation right here correctly represents the valence electrons of group blank. This is the exact same as if in Unit 2 I had said this Lewis dot structure correctly represents what group? Because we're only talking about valence electrons. And I think most people got that one right. Where I would say 1, 2, 3 dots means group 13 or 3A. 1, 2, 3 arrows means group 13 or 3A. Because they have 3 valence electrons. So go ahead, put a box, put +2 extra credit there, and draw in the Lewis dot structure to compare it. Number 20, what group on the periodic table does this valence orbital notation represent? Okay, and I drew this Lewis dot structure as well. 1, 2, 3, 4, 5, 6, 7 dots, just like 1, 2, 3, 4, 5, 6, 7 arrows. 7 valence electrons would belong to group 17 or 7A. The halogens, I could also say. Very similar to what you're going to go ahead and do on 21, the same type of process. Okay, sorry, I was trying to get that focused. For 23, we're using the other side of the periodic table now. It says, which of these elements has the largest atomic radius? So boron, gallium, aluminum, indium. I'm going to look at this side of that green periodic table. You get one like this, not yours, not your copy, but you get one like this on your test. And I'm going to find those 4 elements. And I like to cut up little pieces of paper because you can't write on your test copy. So your elements were boron, aluminum, gallium, and indium, I think. Let me double check that. I can't have both on the screen. Boron, gallium, aluminum, indium. Yep. So they're asking you, sorry, for largest atomic radius. So I'm only going to pay attention to my atomic radius arrows. Big fat francium has the biggest atomic radius on the periodic table. So the closer you are to francium, the larger your atomic radius is. So it increases as you move down the group. So of these, which one would have the largest? I'd follow the arrow and say this one. Indium would have the largest atomic radius because it's in period 2, 3, 4, 5. So it's going to have 5 energy levels to it. Indium would have the largest atomic radius. Well, 24 is using the same skill set, but now we're looking at this ionization energy arrows, okay, or these ionization energy arrows. Sodium, let me get them on here and then I'll show you. Sodium, chlorine, wait, which one? Silicon, sorry, and magnesium, okay. So for highest ionization energy, sodium, chlorine, silicon, like that. Well, ionization energy is largest as you get towards helium. Remember, ionization energy is the attraction an atom has for its electrons. These guys over here do not want to give away their electrons. They have very high ionization energies. So you get largest as you go this way towards helium, which would be chlorine is the furthest following that arrow. So chlorine would have the highest ionization energy. As you do 22 and 25, remember that smallest to largest. Okay, don't get those ones backwards. And that's page 2. Let's move to page 3. Oops, sorry. On page 3, I'm offering some more extra credit for you here. Okay, what I did was I drew how you'd know atomic radius. So I drew the box +2, and then I drew a circle. Radius in geometry and radius in chemistry are the same. The middle of a circle to the outside edge of a circle. But in an atom, the middle of a circle is the nucleus, the middle of an atom, and the outermost part of an atom are the valence electrons. So number 27 says the blank blank is the distance between the nucleus and the valence electrons. You need to have your brain picture this when you read something like that. You can say, oh yeah, that's the radius, the atom radius, or atomic radius. So yes, you need to be able to read these arrows, okay? But you also need to know what each of those 3 things means. Good. I answered some of these ones for you. Take a look at 28 if you couldn't figure it out, or if you made a mistake on it. You can go ahead and change your answers. Okay. For number 29, it says fill in the valence electrons for nitrogen. So just like our Lewis dot structure, we want to figure out how many valence electrons nitrogen has. Nitrogen's right here in family 15 or 5A, so it's going to have 5 dots if it was Lewis dot structure, or 5 arrows if it's orbitals like this. So the first 2 dots go together, up and down, in that first orbital. Just like if we were drawing nitrogen's Lewis dot structure, we'd say the first 2 dots go together, and then 3, 4, 5 by themselves. So up, 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 3, 4, 5 by themselves. Because Hund's rule says they want to spread out into their own orbitals. Okay, remember neon's a noble gas. I gave you a hint to do number 31 on your own. And then I showed you how I did 32. Okay. An atom of fluorine more strongly attracts electrons in a bond than calcium because fluorine has higher blank than calcium. Okay. Well, first of all, resonance, D, right here, that is a chemistry term, but that is not, well, I haven't taught you that. That means it's garbage. Get rid of it. Okay. Fluorine and calcium, it doesn't have a bigger atomic radius. It does have bigger electronegativity and ionization energy. Okay, fluorine has more electronegativity and more ionization energy. But if we're talking about electrons in a bond, we're talking about E extra electrons, which means E electronegativity. All right, let's look at, so you can see how I did 33. I showed you my work. Then 34. Compared to the atomic radius of potassium, so I'm going to put a little thing over here on potassium on my periodic table. I'll show you it in a second. The atomic radius of calcium is blank. Okay, let's stop there. So compared to potassium, calcium would be blank. Is it larger or smaller? Atomic radius is bigger as you get closer to big fat francium. So I can ignore this arrow and say smallest to biggest. All right. So compared, the radius of calcium is blank. Calcium is smaller. Okay. Calcium is smaller than potassium because it's further to the right and it's not as close to francium. All right, which means I can come in and say it's definitely not larger. That goes away. Both of these say smaller, so maybe those are my answers. This is primarily a result of the calcium atom having blank, allowing calcium to pull its valence electrons in closer. Okay, so does calcium have more protons in the nucleus or fewer energy levels? Calcium's number 20, potassium's number 19. So calcium definitely does have more protons in its nucleus. That's true. Does it have fewer energy levels? No, they're both in period 4. They have the same energy levels. So that makes this one garbage, which even if you're not sure that's the right answer, you know that B, C, and D are wrong answers. You took out your garbage and you can say, all right then, I'm going to pick A. All right, so look at the bottom of this. I gave you an example of a 2-sentence answer for 35, and I used all the vocab words there. Number 36 is talking about kind of our nuclear foldable, if you remember making that in class. Okay. Here's mine. Sorry, I stopped to go get it. Thought I paused it. Guess I didn't. But here's my nuclear foldable. Okay. Sorry, we had a little freeze right there, but we're back. Okay. 36 and 37, we're looking at our nuclear foldable. They're talking about which one can be stopped by clothing or paper. Alpha, beta, gamma neutrons. So our alpha particles are our largest. Okay. They can be blocked by paper or clothing. They also don't give you radiation poisoning if there's external exposure. Internal exposure is a different story. But which one can be stopped by clothing or paper? Alpha particles. Biggest, so safest. Smaller, more dangerous. Super small, super dangerous. Not really what we're talking about for those two. Which one can be the most harmful for our cells? That's our gamma radiation. Okay. Gamma particles are only blocked by thick lead or up to 10 feet of concrete. Exposure, they can pass through your entire body, so it causes widespread damage and immediate radiation sickness. Okay. Gamma radiation, when we talk about something being radioactive, that's usually what you're thinking of. Okay, number 40 and 41. When we're balancing nuclear reactions, remember that we're balancing the top numbers and the bottom numbers. So what I have is blank is breaking up into these two things, which means this is fission division. I have something breaking into two smaller things. So x equals 11 plus 0. Well, that one's not too bad, right? Blank equals 11 plus 0. It's 11 on top Okay? And then on bottom, I would say x, right here, equals 6 plus -1. Okay? If you want, just put that in a calculator. When in doubt, 6 plus -1 is 5. Otherwise, you're saying 6 take away 1 equals 5. Okay? And on your periodic table, the symbol that goes with your bottom number is atomic, so number 5 is boron, B. So that's the symbol I would use. Now, in my class, I told students, you beta believe that's the weird one. Beta particles, beta, you beta believe that's the weird one. Because what happens is a neutron turns into a proton. Okay? So this is always, whenever you see this, go back and check your work, because it's the hardest one. Okay? For this one, I'm going to switch colors just so we can stand out a little bit. I have blank, or X, on top, equals 238 plus 4. So 238 plus 4 is 242 on top. Okay. On bottom, X equals 92 plus 2, so that's 94 on bottom. Now my bottom number tells me my symbol, and number 94 is plutonium, Pu. So I would say plutonium would be the missing particle. Beta, neutron, alpha, gamma is not something you have to memorize. All right, so that is something that will be given to you on the back of your test periodic table. It looks like this. It'll be blue and laminated, but it shows you alpha, beta, neutron, and then gamma is just that little G in Greek, right? This symbol looks like a Y to us, but it's G in Greek. Right, page 4. We're doing so good. Talking about nuclear stuff now. Okay. It says, in the equation below, what does the symbol X represent? And now it's multiple choice, so we can take out some garbage. And I'm going to go to this periodic table. I like that one a little bit better. More focused. So I've got promethium, PM, is going to divide into something plus an alpha particle. So I have something that is 154 big. Okay, like it's 154 Legos, and my younger son smashes it, because, yep, and it's going to break up into blank plus 4 pieces on top. So something plus 4 is 154. Well, that something is going to be 150. So my top number has to be 150, not 154. Yes, 150. Yes, 150. Definitely not 158. So I've already taken out 2 things of garbage. Well done. On the bottom, I'm going to say I have 61 protons. We'll break up into something plus 2. So I had 61. It gets smashed. 2 of them break off. What's left would be 59. Because 59 plus 2 equals 61. So 59, 59. That did not help me take out any garbage. But people are going to be like, there's 150 and 59, and they pick it, and they move on, and they're super proud of themselves, and they got it wrong, because almost right is wrong in chemistry, okay? Now I have to notice both of them say 150 over 59. I have to check for symbols. So number 59 on your periodic table is PR, not PM. So when it comes to symbols, that one's garbage. That's my right answer. Okay? For this one, what's the missing particle? On top, let me switch to a good, better color. On top, I have 9 equals 9. Yes, true. Facts. Plus what? Nothing. Plus nothing. It already is 9 equals 9. So I'm going to put 0 on top, which automatically tells me it's going to be that guy. 0 on top means beta particle. But what if I didn't automatically know that? Okay? Then I would say 9 equals 4. No, it doesn't. Or excuse me, 3 equals 4. On bottom, 3 equals 4. False. I'd have to say plus -1. 3 only equals 4, take away 1. and that's E, and you beta believe that's the weird one. I made a proton. That's our beta particle. So if you could fill this in, then you could look at your test periodic table and say, okay, that one is called beta. Beta believe it's the weird one. Something else people go too fast on, just like they go too fast on this one, they go too fast on this one. Fission division. That is extra credit if you write that one down. I'm going to spell division wrong. You just watch me. Okay. Fission, F-I-S-S-I-O-N. Fission division. Okay. I want you to write fission equals division. D-I-V-I-S-I-O-N, I think. I'm so bad at spelling. Okay. But 2 points of extra credit for that. Fission, you're dividing, splitting up. I taught my students that 2 S's are because you have 2 products at the end, like this, one thing dividing into 2 S's. So this one, the process of nuclear fission involves, it's not combining, it's splitting. Boof. People pick B and they feel proud of themselves. That one was easy, and they move on without seeing that right there. Yikes. Okay? It is not combining. That's true. We can get rid of A and D. But B and C both say splitting. Okay, don't go so fast that you get stuff wrong. B says splitting of electrons. C says splitting of the nucleus. Nuclear fission is about dividing the nucleus, not about dividing electrons. Okay? So please, whether it's a chemistry test or a math or English test or your PSAT soon, take out the garbage. Okay? Make sure you're not almost right. Pick the most correct answer. Fission division should help you answer number 47, 48. Okay? I want to look at some more of these ones down here with you. Okay? 50 and 51 get hard, which I like them because I like harder questions sometimes. Nitrogen 15, that's nitrogen with a mass of 15, undergoes alpha decay. What will the reaction look like? Your problem said nitrogen 15,7, and then blank plus blank. But it tells you that one of those that's breaking off is alpha decay. And you should know that an alpha particle is 4,2-He from your foldable or from your test periodic table. So I went ahead and filled in one of my blanks was an alpha particle, 4,2-He. So what's left, 15 on top, I'm going to go over here. 15 on top equals 4 plus blank. So I had 15 Legos. My son snapped 4 of them off. My other son's crying now. How many are left? 11. Okay. So 11 plus 4 equals 15 on top. True. On bottom, 7 equals 2 plus blank. Okay, well, if I said 5, 5 plus 2 equals 7. Good. And number 5 on my periodic table is boron, so I'd say B. That's what the other one looks like. 51 is even meaner. I didn't give you anything. I just told you carbon 14 undergoes alpha decay. So you have to write this, carbon 14. That means 14 is the mass. I knew 6 went on bottom because carbon's number 6. And alpha decay tells me what my first blank is, an alpha particle again. So 4,2-He. Okay. 14, I'm going to divide off 4, which leaves me with 10. 6 on bottom, I break off 2, which leaves me with 4. Number 4 on your periodic table is beryllium. Okay. So I know the top number is 10. That looks good. They all say 10 except for that one's not it. The bottom number is 4. Okay. 4. This one says 6. If carbon has 6 protons, then carbon can't have 4 protons. There's our best answer. Excuse me. Okay. See how I took out my garbage on 52? Okay. And then for your Venn diagram, go ahead and pause it if you didn't know it. Or if you're checking your work, you can pause it. I'm going to go to the next page. The one thing I will say is releases a large amount of energy. You could say that's both of them, or technically fusion does release more energy. So if you put releases a large amount of energy here instead of the middle, that's okay. I understand you. Okay. Let's go to our next page. Page 5. Rewind it if you didn't have time for that Venn diagram. Okay. An atom of the isotope 10,4Be will have, okay, the first thing I want you to know is that number 10 is not protons, neutrons, or electrons. That number is mass. So if anything says 10, I can cross it out, and they don't. Okay. The other thing we remember is protons have to equal electrons. So for A, it says protons and electrons aren't equal. False. Protons and electrons are equal in B. They're equal in C. Protons and electrons are not equal in D. So those are garbage. Okay. Well, Be is number 4 on the periodic table. That's why it has 4 on the bottom. So that means 4 protons, not 6 protons. So 4 protons, 4 electrons. 10 minus 4 is 6, so 6 electrons. That's my answer. Plus, I have already taken the other 3 out as garbage. Okay, 55 is a lot like what I just did with you on 51. Okay, really similar. It says if silicon with a mass of 29 undergoes beta decay, what will it become? Okay, so first thing I did was this. I wrote silicon is breaking up into something and something. One of them has to be a beta particle, which if you just turn your periodic table over during the test, you'll see this. So one of them has to be a beta particle. One of my blanks. Then silicon 29. All right. For this one, I'm going to say silicon is number 14 on the periodic table. So I know this bottom number is going to be 14. And this tells me 28, but that's fine. The problem told me 29. So silicon is going to break off 0 mass, and it will stay 29 on top. So 29, 29, 25, nope, 29. Okay, so I took out one piece of garbage. On the bottom, you beta believe this is the weird one, so go slow and check your work on problems with beta particles. Okay, but 14 equals -1 plus what? Okay, we'd say 15. Because 15 take away 1 is 14. So this one says 15, so that's my answer, right? Whoa, slow down, chill. That one says 14, so that's not the answer. Because 14 take away 1 is not 14. I already said that one was garbage. That one also says 15. So I've only eliminated B and C so far. So then I look, number 15 has the symbol for phosphorus. So this is my answer, even though that one's almost right. Okay? Almost right is wrong in chemistry. If you almost mix the right chemicals, that's a good way to be dead, right? Almost right's wrong. Okay, let's look at some of this nuclear graphing stuff down here. So we're looking at, my papers are everywhere. Number 58. An atom of the isotope 120, 50 SN is likely to have, so I already did this. 120 minus 50 equals 70 neutrons. So I said that top number can't be right. So it's going to be 70 neutrons, so C or D, but will it be stable or radioactive? Now we need to graph it. Okay. So 50 protons, right here are my protons. 50 of them are protons, so 40, 60, 50 protons, and 70 neutrons. Neutrons are right here. So 60, 80, that makes this one 70. If I graph that, that's pretty dang close. Okay. If it's that close, we're going to go ahead and say stable. That one's going to be stable. If it's out here, we'd say radioactive. If it's way out here, we definitely say radioactive. So we're going to pick that one. That feels good. Number 59 says the element tellurium has 52 protons. Could stable isotopes exist? Okay, well 52 protons is going to be just above this pink line. Okay, kind of like, I don't know, right here. Draw really carefully and slowly. Yeah, it's possible for it to be stable. If it's got like 100 protons, no, there's no stable options. But at 52, yes, it could be stable. So that means this one's not my answer. With about how many neutrons? Well, it's stable in here. Okay. Uh-oh. Did I do that wrong? No, we got it. Okay, we're good. Okay, so with about 52 neutrons, right about here, that would be radioactive. We're looking at 52 neutrons, so that can't be it. Okay, B with about 88 neutrons, that'd be right about here. That one would be radioactive. Okay, with about 68 neutrons, right about here, okay, just before 70, that's in the stable area. So I'd say, yeah, C looks good to me. 60 is another one that people get wrong sometimes on this and on their test. It says the element calcium has 20 protons. Can stable isotopes exist? So at at 20 protons, yes, it's possible to be stable. So I'm going to say yes. With about how many neutrons? Well, it looks like, I don't know, 20, 21, 22. So I'm going to say 20 to 22 neutrons. Somewhere in there. It could be stable. Then 61. I'm going to put a big star by that. Electromagnetic waves. We did that the last day of our notes, the day we did the flame lab. It's also what we're going to talk about on page 6. But it says electromagnetic waves all travel at the same speed. Whether that's infrared light or gamma radiation or blue light or green light, they all travel at the same speed, the speed of light. They have different amounts of energy, L-I-G-H-T, but they travel at the same speed. So let's go here, okay? Here is some extra credit for you, okay? 2 points of extra credit for copying just this top stuff. Higher frequency equals higher energy, and high energy means dangerous, radioactive. So over here you see how often these lines, they're going up and down really frequently. High frequencies, gamma rays, those are dangerous. High energy. That's something to memorize, so give yourself extra credit for that. This stuff I wrote here to the sides. I added in class with my students. I'm not sure if your teachers did, but it's a good idea. Okay, where I said on this side of my electromagnetic spectrum, I have a long frequency, so high frequency. Oh, sorry, long wavelength. I'm pointing to it. Long wavelength. See how long the waves are? Over here, the waves are really short. So I said low or short wavelength. And then I said high frequency is over here. They're repeating. Over here, you're a lot less frequent. And then I put the energies there. So that information should help you answer the first 2 questions. And then we're going to look at some of these other ones before I give you your last extra credit. Okay? It says, number 64, what's the relationship between frequency and energy? And we really said that up here already. High frequency means high energy. So those arrows will both be up over here, or they will both be down over here. Radio waves are safe, and they are infrequent or low frequency. So if the arrows go in the same direction, they get high together and they get low together, direction would be a direct relationship between frequency and energy. They go up together, or they go down together. Number 65, if frequency increases, what happens to wavelength? Well, it says here low frequency, long wavelength. High frequency, short wavelength. And look at my arrows. I did this. Up, down, down, up. They're opposite. So if frequency goes up, wavelength must be going down. It decreases. If energy goes down, what happens to frequency? Well, we already said that here. Energy and frequency go together. So if energy is decreasing, frequency goes in the same direction, it decreases. And then number 67 says, what's the relationship between frequency and wavelength? Unlike this one where they go up together and down together, frequency and wavelength have opposite directions. If one arrow is up, the other arrow is down, or inverted. We call that an inverse relationship. go back and watch the video tutorial for pages 10 and 11, I think, if you need more help on this type of stuff. Okay. The very bottom. We did this Spotlight Scientist in class in your notes. If you were absent, just write that you were absent here. You should have this all filled out from that. But for your last 2 points of extra credit, go ahead and write where it says Marie Curie, say is awesome. Okay, she was pretty hardcore. And if you were there, I hope you guys can appreciate how, I don't want to say bad A on a video, right? But she was pretty hardcore. All right, thanks. Good luck on your test.